Hi everybody. In this video I want to do an example involving Faraday's law of induction. Here's the example. Imagine I have a conducting loop of wire of resistance 0.0700 ohms. Imagine this loop is actually a rectangular loop defining a rectangular area, and it has sides with these dimensions. Imagine this loop, this rectangular loop, has been placed in a uniform magnetic field. The direction of the magnetic field is this way as shown. That direction of the magnetic field makes a 50-degree angle with the plane of the loop, or a 40-degree angle with the area vector that's perpendicular to the plane of the loop. All right, let's further assume there's no battery or power supply of any kind in this loop. It's just a loop of wire that's been placed in a magnetic field. However, let's assume that this magnetic field is changing. Let's assume it changes from 2 Tesla in this direction to 5 Tesla in this direction in a time period of 60 seconds. All right, so our job is to determine the average induced current in the loop. And I say average because we're not given any information about the pace at which this change takes. We just know at the beginning of the 60-second interval, the magnetic field has a strength of 2 Tesla, and at the end, it's got a strength of 5 Tesla. So the best we'll be able to do is calculate an average induced voltage and then an average induced current. All right, why is there going to be a voltage and current in the first place? Well, if I've got this changing magnetic field, that's going to give us a changing magnetic flux. Remember, magnetic flux is an integral of magnetic field dA integrated over the full surface. For the case of a uniform magnetic field, which we have here, we can pull the magnetic field vector out of this integral. The rest of the integral dA gives us area vector. So this dot product here gives us the magnetic flux. That's going to involve the magnetic field strength, the area, and the cosine of the angle between the magnetic field and the area. The area is not changing, the angle is not changing, but the magnetic field strength is. So that means the magnetic flux will be changing. If magnetic flux is changing, we have an induced voltage. We don't know the exact rate at which this stuff is happening, so we're going to go over from this version, the exact version of Faraday's law, to the average version by changing the differentials to deltas. Now, Faraday's law gives us the induced voltage. This problem asks us for the induced current. All right, so there's one more step we need to think about. So set this aside for a moment and think about just a regular basic garden variety circuit. Just a circuit consisting of a battery and a single resistor. All right, there'll be an increase in potential across the battery and a drop in potential across the resistor. Voltage drop across the resistor, remember, is given by the product of current going through the resistor and the resistance of the resistor, I times R. Okay, so the voltage drop across the resistor is current times resistance. The voltage drop, the amount of volts lost across the resistor, is equal to the amount of volts gained across the battery. So by putting all that together, I can say the voltage gain across the battery, like if it's a 30-volt battery or whatever, will be equal to the product of the current and resistance, with the current going, in the direction shown. Okay, we don't have a battery here. Instead, what we have is a voltage produced by this Faraday's law process, this changing flux. Changing flux produces an induced voltage. All right, so what we're doing, this conceptualization is like this, except that instead of having a battery, we're going to have this Faraday's law process that's basically taking the place of the battery. All right, so instead of having the potential difference across the battery terminals being equal to the product of the current and the resistance for a single battery and single resistor, what we're instead going to have the situation where instead of a battery, we've got voltage produced by this changing flux. And then the resistance, there's not really like one little resistor here. The resistance is basically spread all the way throughout this wire, but we're just going to model it as being in one place. All right, so instead of battery voltage turning out to be equal to current times resistance, in this simple case, we have a similar simple situation. Instead of a battery, we have a Faraday's law voltage, and then we have a single resistance spread throughout the wire. All right, so in our calculation, we can replace the average induced EMF, the average induced voltage, with the product of the average induced current and the resistance. All right, so with all of that, we can get started on the problem. So I'm going to work with this average version of Faraday's law. So I'm going to replace the average induced voltage with the average induced current times the resistance. And then so that's the left-hand side of this average version of Faraday's law. On the right-hand side, what I'm going to do is plug in for the magnetic flux. The magnetic flux is this product over here. So I'm going to put all that inside the delta. Okay, now I can do two things when I go to my next step. First, I'm going to divide both sides by the resistance, but what I'm also going to do is I'm going to pull some things out of these deltas. Deltas in differences are treated the same way as derivatives are. That is, we can pull constants out of a derivative. We can also pull constants out of a delta. So this area, that's not changing. Cosine theta, well, this angle's not changing, so cosine theta is not changing either. The area and the cosine theta can pop out of this delta, so I can pull those out. And this thing at the top is just going to be minus a cosine theta delta b. Meanwhile, I'm going to divide both sides by r as well. So here we go. Okay, so now all I've got to do is plug in for all these quantities and I can determine the current. So the area will be 0.2 meters multiplied by 0.4 meters. Cosine theta, that'll be cosine of 40 degrees. Delta B, we've got to be careful. We went from 2 Tesla to 5 Tesla. Both of those were in this direction. So the final amount was 5 Tesla this direction. The initial amount was 2 Tesla this direction, so I'm going to have 5 Tesla minus 2 Tesla. I'll plug in 3 Tesla for delta B right here. The resistance of the loop was 0.700 ohms. The time was 60 seconds. You might be tempted to put 1 minute in there, but then you'll mess the units up. If all of these are in SI units, then the current will come out in amperes. All right, so I need, for this time interval, I need 60 seconds. So if you plug all that in, you will get this value. Or if you want to change that to milliamps, minus 4.38 milliamps. Okay, now we need to interpret that. I've got a minus sign, but what does that mean? Well, if you're not careful, it won't mean anything. If you've been really careful, the minus sign will allow you to figure out the actual direction of the induced current. So here's how that works. Assuming we've taken this direction here to be our area vector, remember there is a right-hand rule relationship between the area vector corresponding to the area of a surface and the positive path around the perimeter of that surface. So remember, right-hand rule. Stick the thumb in the direction of the area vector, fingers wrap in the sense of the positive perimeter direction. Well, the positive perimeter direction would also be the positive, if you have a positive current, that's the way the current would be going. So thumb in the direction of the area vector, fingers wrap around. If the current were positive, the current would be going across the front and then left across the back and around. But my current came out negative. So my current must be going the other way. So I can represent that as follows. I'll represent this here, and then I'll note that I average absolute value is equal to 4.38 milliamps. All right, so then I don't have this ambiguity. I know the amount, and then this arrow gives me the direction, and that's the current that's been produced. Okay. All right, I want to make a couple of further comments. The first comment is we need to be careful about this step right here when we've got ourselves a delta B. If we had had 2 Tesla in this direction and then 5 Tesla in the other direction, so let's say like maybe the magnetic field was in this direction, but it was decreasing and decreasing and decreasing and then went to 0, then went to 5 Tesla in the other direction. There would be a hidden angle change there. The initial angle would be 40 degrees, but once the magnetic field is this direction, there's a different angle between the area vector and the magnetic field, and we need to account for that. Doing that here, we'd assume the angle hadn't changed. So if there's more than one thing changing, it's rather than doing these tricks here, it's safest to just say, I'm going to find my initial magnetic flux. I'm going to take my initial magnetic field strength, the initial area, the initial angle, grind that out, get your initial flux, then do that for the final state. Put in the final magnetic field, strength, final area, final angle, and then you get your final flux. Take your final flux minus your initial flux. That would be this step here. Delta flux, final flux minus initial flux. All right, so you can always do that. You don't always need to do these tricks. In fact, you could handle all of these things changing as long as you take the final one minus the initial one. All right, so that's the first pitfall. So the last comment I want to make relates to the direction of the current. You might ask yourself, wait a minute, we had this changing flux, and this changing flux ultimately produced an induced current. But this current itself should be producing a magnetic field. What if that current had an effect to produce more flux in the same direction as the initial change in flux, producing more current, producing more flux, producing more current? You could have a runaway process. That would be a real problem. So let's first check and make sure that this hasn't created a runaway process. So let's first consider the change in flux through the loop associated with this changing magnetic field. And I want to emphasize it's the change in flux that matters, not the flux itself. All right, so initially we have a 2 Tesla magnetic field this way, which is producing a flux up and through the loop. We then go from a 2 Tesla magnetic field to a 5 Tesla magnetic field. So we've got more magnetic field and hence more flux up and through the loop. So we go from having some flux up and through the loop to having more flux up and through the loop. So the change in flux is up and through the loop. So the question is whether this induced current opposes that change in flux or augments it. Let's check. The induced current is to the left across the front of this loop. So let's use that to check. I'll stick the thumb of my right hand in the direction of the current. My fingers will wrap around, and in the direction at the center of the loop, my fingers are pointing down. So this induced current is producing a downward magnetic field and hence a magnetic flux down and through the loop. All right, so the flux associated with this induced current is down and through the loop. That's opposed to the upward and through the loop change in flux that produced the current in the first place. This principle that the induced voltage and induced current should have an effect that opposes the change in flux that produced them in the first place is known as Lenz's law, and I will cover that in another video. Thank you.